start. The plan for today is to finish the topic of pipelining. Next, we will go through, we only have next week. The plan for next week is to discuss out of order execution. And that's the end of the story for this version of the course. Even though there are some other exciting topics in computer architecture which I would have loved to discuss, but the time is limited. Before we start, do you have any question for me that I can answer? Hopefully you look at your grade for midterm, and if you have any question, if you want regrading, please do that through Gradescope, and you let the TA know about it, and it will take care of it. Okay, so if you remember, we finished off on Tuesday discussing these fundamental ways of handling flow dependence. The plan is to elaborate, so rather than saying what it is, to discuss and give you some idea how this is actually done in practice, more on the approach side. So detecting the dependency between instruction, as you know, guarantee the correct execution, and we discussed why and how. If you remember, we discussed a particular example on Tuesday where, without considering this dependency between instructions in a pipeline processor, things may go wrong. Basically, one instruction may write to a register, and other instruction depends on a previous value, or the follow-up instruction may need the value of a particular register that has been written by the previous instruction, and that write has not happened yet. So these are, and now is the time for reading this value, and it's not available. So this kind of situation is what we call dependency, and we discussed like 3 variations of dependency. And in terms of solution, there are different approaches, methods that has been proposed and has been implemented, both at the software level and hardware. Basically, these are known as software-based interlocking and hardware-based interlocking, which somehow the MIPS acronym comes from. And if you remember, to giving you some intuition, we discussed about that. At least we discussed very high-level idea how this can be done, like at a compiler level, and at the hardware level, we'll discuss a little bit today how this can be done. And as you expect, there would be some need for adding some data paths. So there would be extra thing that needs to be taken care of. One of the important approaches for detecting dependence is scoreboarding, which is somehow an interesting approach. So in this case, each register in register file has a valid bit. So imagine that we consider one specific bit in each register associated to valid bit. And valid bit is we want a binary value, essentially, meaning that we want to indicate whether we can write to this register or not, right? An instruction that is writing to the register reset the valid bit. An instruction in the code stage check if all its source and destination registers are valid, because like in the next stage, these values are forwarded for execution. So in order to do any ALU operation, this value needs to be valid, otherwise the result would be correct. So somehow this Boolean value, whether this register value is valid or not, is one solution. Somehow has obviously some advantage and disadvantage, but it's straightforward. How to implement it is just adding a bit into the registers. So in this case, there wouldn't be any need to install the pipeline. If this bit is valid, meaning that the instruction can move basically, and if the register is not valid, meaning that we need to install this instruction that is at the earlier stages. And you know that we want to install the young instruction, meaning that those instructions who came to the pipeline recently. If you think about the pipeline, at the same time, multiple instructions, some instructions are doing later stages. These are the old instruction that has been there for a while. Some instructions are new and has entered to the pipeline recently. So advantage is simple, as you can guess. It's just a bit per register. Disadvantage is that we need to install all types of dependencies, not necessarily only flow dependency, which was essential. In this case, all type of dependency needs to be detected, and the corresponding instruction needs to be installed, which is not really which is not ideal, because again, this flow dependency was the essential thing that violated the semantics of the execution. The other ones had an easier solution because they were not an essential dependency. They could be resolved by just renaming these register values. But in this case, like, we rely on this one bit, so all type of dependency will be detected as a result, and install happen for them. I hope this is clear, right? If you want me to explain further, I can do that. But this idea of a scoreboarding is easy to understand. I don't know why it says that my connection is not stable, but hopefully you can hear me well. So the way how you can think about this, how this actually can happen, we can do that through adding some combinational logic. to realize this for us. And these logics are easy. Checks if any instruction later stages supposed to write to any source register of the instruction that is being decoded. So again, like some instruction in the pipeline are in the later stages. And if you remember the example that we had, this 4 instruction example that we had last time, you will see a little bit later again. Some of these instructions are later stages, and they're supposed to generate a value that, for example, the first instruction was adding the value of 2 register right into another register, and the second instruction was an AND that required the value of the value that has been generated in the first instruction. So in this case, we check if any instruction later, for example, in this case, add, is supposed to write to any source register, like the source register that second instruction was dependent on. And the second one, at some point, let me go back maybe to examples, so hopefully you recall what I'm talking about. So here, the first one, adding S2, S3, putting into S0, and then the second one, third one, and the fourth one needed the value of S0 as one of the 2 arguments. And we discussed that the first instruction in the pipeline, the write or the value of S0 become valid in this case, in this terminology, after this T5, right? At this time, after 5 cycle, and we needed the value in T3 because the instruction is being decoded there. In T4, we needed to feed this value to ALU. Would otherwise the result of the second, third become invalid, and the fourth one is simply good to go. So in this case, if that's the case, we need to install the instruction in the pipeline. If it is no, if like by these combinational dependence check logic, if that's not the case, then we don't need to be worried about that because there wouldn't be any dependencies. Advantage is that no need to install on anti and output dependency, and disadvantage is that logic is more complex than the scoreboarding. In this case, let me see whether we have a slide for this. In this case, it would be we need additional combinational logic in order to check that. In particular, maybe let me see whether I should use iPad. Maybe I can explain it on the example itself. So here, you have in the register file, you have S0, right? And here we see that S0 in the argument of the follow-up instructions that come into the pipeline at some point, enter the pipeline at some point. if we add a combinational logic, and by combinational logic, any gate that, for example, determine the equality of two values, two entity, right? For example, say if we forward the input as the input to this combinational logic, the index of these register names, right? Then we could detect whether any following instruction actually depends on this value through logic, through checking the index of two registers that comes from the argument of these instructions. If they are equal, in this case, like you see that we have S0 here, and we have S0 in the second one, S0 in the third one, and S0 in the last one. So in this case, like we forward the 0 as the index, and then all others, if you have a logic to compare this index, we at a hardware level, and this is through combinational logic through hardware, we can right away see whether there would be a need to stall instruction or not if these indices are exactly the same. If not, there is no need to stall. And the difference is that in the other approach, scoreboarding, you only needed to check whether the value of this bit is valid or not, meaning that it's 0 or 1. That's it. There wouldn't be any combinational logic to compare two indices. So it's simpler in the case of the second approach that is based on the combinational logic. So hopefully this is also clear for you. But in this case, as you can guess, we have more flexibility, meaning that we do not need to install on anti or output dependency as a result, because the information that we collect in this way is more, and we can detect these type of dependencies and stall accordingly. So as a result, we would have less number of stalls in the pipeline, which is a good advantage. But as you can see, this logic becomes more complex because we need to have more information, obviously, and this information actually is having and knowing the dependency not only within the stages of a pipeline, meaning that different stages, like the current instruction, which is like supposed to write to a register, is not written yet, but also through dependencies between instructions themselves. And that's why you see deeper and wider. Deeper meaning that having a more number of stages that you need to do, and wider meaning checking the dependency between instructions. once you detect that, the question is that what do you do afterward? An observation is that the dependency between two instructions is detected before the communicated data value become available. This is like the problem basically in a formal way. Option one is stall the dependent instruction. So in this case, like if you think, like we have two roles. One instruction is dependent. Other instructions basically is not dependent on this, is actually created this dependency because supposed to generate a value. Make sure that you understand these differences in terms of role. And option two is to stall the dependent instruction only when necessary, which is a lot better rather than blind stalling. We can, if you remember, we can, as soon as we generate the data, we can bypass and move the value for the next instruction whenever the next instruction needed this value. And I mean, before we go to make it clear, how this will happen. So to remind you, so in this case, add the add result, the value of S2 plus S3 become available or will be generated at T3 and become available at 4. Cycle 4 is when the second instruction exactly needed this value. So this value can be after it has been latched at the start of this cycle 4. You can pass it or forward it to the ALU. Here you see we need value as 0. And we need to have this again at cycle 5 for OR instruction. So we can do this forwarding again for the last instruction. This is good to go because we, in the first half, we read from the we write to the register, and in the second half we read from the register value. So this is good. There wouldn't be any forwarding, explicit forwarding needs to happen. And this is how it gets implemented at the hardware. So few things that has been added, as you see, in terms of forwarding. First of all, we need to have additional input to these muxes. So let me go. Yes. So here you see that you see a new data path between here and here. So the ALU would require additional input, and you need to extend these muxes that coming to the ALU. Here you see that these two muxes, previously we get one input from this latch and one input from here, right? One input from here. This is the case where this forwarding will happen, and we need a hazard unit that we also need to have new control signal. These are stuff that will be sent as an input to this muxes, right? So you see this forwarding value. These are the exact same value that has been generated in previous instruction and needs to be forwarded to the next instruction whenever it is needed. So the takeaway is that we need additional data paths at the hardware level, which we did not have them in order to take care of this data forwarding. And this, you see the connection here as well to this hazard unit. As you can guess, these are needed in order to check, because this hazard unit check whether any dependency exists or not. And in that case, through this combinational logic, so we need this information. What are the exact register that is needed in or is used as an argument in the instructions. So these are that's why you see like some of these additional data paths as well here. And obviously, and if you think clearly here, these forward values may happen in the memory stage and in the write back stage, right? So in this case, for writing to OR, and as a result, you see here, so in decoding, there wouldn't be any additional need to add any data passes, right? So the only stages that needs a new data pass is this execution stage where you have ALU doing ALU operation and write back. So we had a particular example that during this stage needs to be this value needs to be forwarded to another instructions. So that's how this is happened, right? So we have one data pass from data writing back stage to execution stage, and one from basically simply from the execution itself, and some control signal that generate, okay, like when and what input should goes through this and come out of the mux. So hopefully this makes sense to you. Okay. And as a result, we get less stalling, as you can guess, because simply as long as we are able to forward any value that is already out there to the instruction that needed this value, we are good to go. But so as a result, we need less stalling. But it doesn't mean that we don't have any stalling, because there are situations where simply the value of some instructions that has entered into the pipeline is not been even calculated yet. There would be some instruction basically need to be installed at some point. And beside data dependency, there is also control dependency, which is very similar to data dependency. Control dependency is basically what the question is that what should the next PC value, right? What should the fetch PC in the next cycle? The answer is that yes, the PC value, and PC, if you think about it, PC is just a register similar to the register that you have in the register file. So you can think about this as a special case of data dependency, because there we're talking about the dependency between the instruction that deal with the registers. PC is also a register, so you can think about it as a special case of data dependency, but with some differences, right? The answer is the address of the next instruction, and that's true. And in some special computer like MIPS, we know exactly the address of the next instruction, even though this is not a generic thing. So there's no guarantee in all machines we know the address of next instruction. We know the address of next instruction in MIPS because all instructions have the same length. But this is MIPS, and this comes with the design. In some machines like x86, the length of the instruction would vary. Some instruction are lengthier, some instruction are shorter. So not all the time we can know the address of the next instruction. We may be able to calculate it, but it's not easy. But anyway, like in MIPS, if the fetch instruction is a non-control flow instruction, meaning that is like a add or this kind of instruction is not one of these control instructions that you are aware of. So the next PC is the address of the next sequential instruction. MIPS is PC plus 4. So it's easy to determine if we know the size of the fetch instruction. If you don't know, it's tricky a little bit. And if the instruction that is fetched is a control flow instruction, then the problem is that how do we determine the next fetch PC? And one may say that, okay, based on the logic of the program, if this is a like BQ kind of instruction, so at some point we know exactly where we want to jump into. But the thing is that yes, but before we reach to the state that we can infer the address of the jump instruction, we want to know exactly what that value is, or we want to determine the next fetch PC, but we simply don't know it yet because this instruction has not been decoded yet. Okay. Simply because we haven't decoded it, so we don't know whether this is a control instruction or not. And if you remember, we discussed these type of dependency. This is again another pipeline where basically we have this instruction. All of them are add I type of instruction, and we have this dependency where in the first instruction, this register address has been written, and then we need to use that in another add I instruction, right? So there are some dependencies between all of these instructions and the first instruction. And even though you can think about multiple different resolution, as we discussed, like there are some formal solution that consider the distance of two instructions based on some calculation, and then can predict whether a stall can happen, or how many additional no-op instruction we can insert into the pipeline in order to resolve this issue, right? In this case, for example, here we write we write to the register in T4, right? And then based on this and based on the number of dependency that we have, right, in the follow-up stages, in this instruction, if we have this write first and read second, then there is no dependency here. But in others there are. And based on the distance between these instructions, we can calculate how many no-op operation we can insert into two consecutive instructions to resolve this issue. So in this case, after we fetch the instruction J in T2, we need to insert 3 additional no-op operation, meaning that we need to stall this instruction 3 cycles, and then it can continue moving forward after 3 no-op operation. So based on this distance value, you can calculate the number of no-op operation you need to insert into the pipeline. And we discussed previously about the intuition why we want to stall the young instruction and finish the later instruction, because it increases the throughput. Otherwise, if we do this differently, if we stop the old ones and carry out the young ones, then the throughput will decrease as a result, and this doesn't make sense. And the way how this stalling can be implemented in the hardware is not difficult. So obviously we need to have some logic, additional logic, to determine whether a stall needs to happen or not. But how the stall can happen at the hardware level, you can disable the PC and this latch once you need to stall a particular instruction. So meaning that you don't want to change the value of a PC. A stall has happened, you don't want to move or add additional instruction into the pipeline. So meaning that the pipeline has to stop, meaning that you should not allow writing to PC. And also this latch needs to be disabled, because you don't want the instruction, here you see that this instruction J has been fetched, but you don't want to move forward to decoding, because simply there is a need for stall here. So the this instruction J, which is based on a particular value, can use this value after 3 additional no-op operation. So after this alignment, basically. And this is the case where, again, we do not incorporate the forwarding value. Here we assume that we have to write to the register first before we are able to proceed with the dependent instructions. So if we take care of this disabling PC and this IFID latching, then we can make sure that a stall has happened, but also we need to insert some no-op operation into the stage after we detected a stall needs to happen. And this no-op operation, hopefully you know, can be generated by simply some special control signal that the machine or the CPU would produce. Okay, we discussed about this before. And this is another schematic version right here. Again, this is the example that we discussed several times. So if we add these 2 additional no-op, this no-op doing nothing, then these 2 consecutive instructions become aligned. So basically here at cycle 5, we have the correct value of S0 sitting in S0, and the second instruction, this add, can proceed. But you see that we need to add 2 additional no-op, which is not ideal. And a better idea maybe is to forward this value whenever, at what stage, when they needed it. Yeah, we discussed about this. Let me see. And this is the logic for generating this forward AE signal. This forward AE is exactly this this signal. So this this will say that if this RSE signal is not equal 0 and RSE is equal to write register M and register write M, then forward AE is 1, 0, meaning that we want to forward from memory stage. And if this is true, and you see this write register M, write register W, so in this case, meaning that we want to forward the value from write back stage. This is 1, 0. So sorry, 0, 1. 1, 0, 0, 1, and no forwarding 0, 0. So if you Where is this? So if you look at this, so 1, 0, meaning that this is forwarded from memory stage. Okay. If 0, 1, meaning that this value is forwarded from write back memory, write back stage, right? And 0, 0 is normal data path that we had before, is coming from the previous stage, meaning that no forwarding will happen. So now hopefully this data path and the way how you can generate this signal, because the most important signal in this new hardware or this updated hardware is this 2 signal that you need to generate. Forward BE is also the same. So these are based on this write register M and write register write W. You can generate the forward AE accordingly. Yeah, and forward BE is also same. You need to change it RSE with RTE. So basically these are register source, register target, control signal for forwarding. But again, even if we have this additional hardware to enable data forwarding, it's not the case that we have 0 stalling. In this case, in this example, we have load word. We need to have access to the memory and load the content into one particular register S0, and then here we need the value of S0 in this case. So if you look at the logic, we are able to give this instruction after cycle 4, but the next one required this instruction right at the beginning of cycle 4. So this cannot be done without any stalling. Or stalling, or like moving some of these independent instructions up. In this example, all of these are dependent. So in this case, here it's good. This can happen without any stalling. The last one is also good to go. There wouldn't be any problem there. But some stalling technically needs to happen. So in this case, we need to detect, and this can happen through detection. It's not straightforward. This stalling should happen. So we have a combination of data forwarding in this example and stalling for this dependent instruction. Okay. Let's stop here. We discussed what we wanted to discuss about pipelining. So I guess we have covered good part of pipeline. There are some additional advanced algorithmic or formal approaches in pipelining. Again, pipelining is a strategy that increases performance. There is no unique way. It's a kind of a scheduling problem. And for those who know about the scheduling as a mathematical problem, should know that is an optimization problem. So, and there wouldn't be unique. There is an optimal answer for a scheduling problem if we fully know the space. But but it's not the case that given the current information that we have, we can come up with the perfect pipelining. We cannot guarantee any even perfect scenario that we fully utilize the pipeline. So there are some fragmentation, but different approaches come up with some mathematical and algorithmic innovation to reach the optimal point as much as possible. There wouldn't be any guarantee about optimality in this case, but many approaches have tried to address this as much as possible and push the state of the art forward and get better result. But let's stop here, and then we move forward with out of execution next week. I'll stay here for a few minutes. If you have any question, I would be happy to answer. Thank you.